Welcome back to this next video in which we are discussing field extensions. Okay, so in this video what I'm going to do is firstly tell you about a few more definitions regarding field extensions, and then what we're going to do is prove a really important theorem about field extensions. Okay, and we'll end then. Right, okay, so firstly a little bit more notation, a few more basic definitions that we're going to need in order to understand this really important theorem that I've got. Okay, so let's say that we've got K, which is a field extension over F. Okay, so drawing a little picture here, the larger box here will represent the larger field, capital K, the field extension, and then this will represent our original field at capital F. Okay, the smaller field. So I'll colour in F in orange here, and then the field extension will have circled in green, like so. Okay, right. So, what we're going to need for this new definition is a few elements that are in the larger field extension K, but are not in the smaller field F, the original field. Okay, so I'm going to call these elements alpha 1, alpha 2, and we'll go all the way up to alpha n, where little n is some finite number. Okay, and of course this isn't the same n that we've been talking about all along as the degree of the polynomial p of x. This is just some other little natural number. It's just my favourite letter, and most people's favourite letter, for denoting some arbitrary natural number. Okay, so a1, a2, all the way up to an then. These are elements of the larger field capital K, which are not in the field capital F. So they're elements of K without the field capital F. Okay, right. So what I'm now going to define is what's called the field generated by these elements alpha 1, alpha 2, all the way up to alpha n over F. And it's denoted, and I'll write it here, F and then curly brackets, alpha 1, alpha 2, all the way up to alpha n. And you just read this F of alpha 1, alpha 2, all the way up to alpha n. Okay? In full, this is called the field generated, so I'll give its full title. If you want to give it its full title is the field generated. So this is a field, this thing is denoting a field. The field generated by these elements alpha 1, alpha 2, all the way along to alpha n, and then we put over the field F. So it is in fact going to be a field extension of the field capital F, the smaller field. Okay, so I'll colour it in pink here. Okay, so this is going to be defined, this is the definition of this. This is the smallest subfield of the larger field capital K that completely contains the field capital F. So it has to completely contain capital F as a subfield, but it also has to contain all of these elements alpha 1, alpha 2, all the way up to alpha n. And I'll repeat that this is a subfield, not necessarily a proper subfield of the field capital K. Okay, so this is what I mean by the field generated by alpha 1, alpha 2, all the way up to alpha n over F. Okay, it's the smallest subfield. So if I try and mark it on here, the picture, don't take the picture too literally. I'm just going to mark it on like so. Okay, so the picture is literally just denoting this. Okay, don't take it as it actually contains like 5/6 of the elements of capital K. Don't take the sizes literally, basically. Okay, so here it is. Here is my field generated by alpha 1, alpha 2, all the way up to alpha n. It is a field that is in between these two in size. It has to completely contain the smaller field capital F. That's why we put this over F here. That's showing that it's a field extension of the field F here. And it has to contain all of these elements which previously weren't in F. These alpha 1, alpha 2, all the way up to alpha n. And because it's the smallest one that contains those, we can think of it as all the information about it is coded in these elements, hence why we call it the field generated by alpha 1, alpha 2, all the way up to alpha n. All the information you need to describe this field is just that it has to contain these elements and the field capital F. Okay, so here is our larger field capital K, and here is our smaller field capital F. Okay, so the field generated by alpha 1, alpha 2, all the way up to alpha n is the smallest subfield of the larger field capital K that contains the smaller field capital F and all of these elements, alpha 1, alpha 2, all the way up to alpha n. So to stress this even more, I will actually write that this field, the field generated by alpha 1, alpha 2, all the way up to alpha n over F, is actually a field extension of F. Okay, so there is the definition of the field generated by a whole bunch of elements, alpha 1, alpha 2, all the way up to alpha n over another field, capital F. Okay, right, so there's that definition. Now another definition, the definition of a simple extension and a primitive element. Okay, now we're not going to need the concept of a primitive element really in this video. It's going to become really important later on, but I'll give you it because this is kind of our introductory video. Okay, so I've had a very general definition here. I've had an arbitrary number of elements that you're trying to put in, basically, okay? But you can just do this with one element. So now let's say we just want to generate the field over F that contains a single element. Okay, so we might want to put in alpha here. Okay, so this is the field generated by this element alpha over F, and this is going to be a field extension of the field F, and it itself will be a subfield of the larger field capital K. Now, if the field that you're generating is generated by a single element in this way, okay, if this field extension of F is generated by a single element, alpha, then we call it a simple extension. So a simple field extension is one that is generated by a single element alpha, okay, and that's how you build it. So you should imagine initially that we're working with some larger field K. So again, there is some larger field K. F is a subfield of this. Alpha is some element outside of F that's in K. And then you're trying to find a subfield of the larger field capital K that contains alpha. Okay? And that subfield will then be a simple extension of the field capital F. Okay, so let me just give you an example of this. So we know that the complex numbers is a field extension of the rational numbers. The rational numbers is a field and it's completely contained within the complex numbers. Of course, the complex numbers is a much bigger field than the rational numbers. Okay, what we can do then is we can take some element that's in the complex numbers that isn't in the rational numbers and say, let's generate the subfield, the smallest subfield that contains that additional element. Okay, so for instance, you could say, let's build the field generated by the square root of 2. The square root of 2 is not found in the rational numbers. It's something that is in the complex numbers. Okay, this would be a simple extension of the rational numbers. It would be a field extension of the rational numbers, and because it's generated by a single element, it would be a simple extension. In addition, we could say, I'd quite like that imaginary number I. Okay, so we could build the field generated by the imaginary number I over the rational numbers. These are examples of simple extensions of the rational numbers. Okay, and initially when you understand this, you should think of it always as being contained within some much bigger field, and we can pick some elements from that much bigger field that we'd like to have in, and then we can find the smaller subfield of that larger field that contains all of the field F, the tiny little field, in this case the rationals, and that additional element that was outside of the initial field F. Okay, final definition then, and then we'll look at this really interesting theorem. This element alpha that generates this simple extension, this is known as the primitive element for this extension. Okay, so if you've got a simple extension, then of course it will need to have some primitive element. So a primitive element for a simple field extension is the element which generates that field extension of the initial field F. Okay, so alpha would be called the primitive element. In this case, of course, the primitive element would be the square root of 2. In this case, the primitive element would be I. Okay, so only 3 definitions then. The field generated by a bunch of elements, a simple extension, and a primitive element. Okay, so those are some important definitions that we will see time and time again later on in the playlist on field theory concerning field extensions. Now then, let's talk about this really important theorem. Okay, and this is going to go now back to the thing that we have spent so long constructing, this field extension which contains a root to our irreducible polynomial p of x. Okay, so here comes this really important theorem, so I'll put it as a great claim, and then what we want to do is prove this claim. Now, the first task is just to understand why this claim is so important and why it's so deep. Okay, and I think to do that we'll have to look at an example, and then what we want to do is prove it. And then finally what we'll have a look at is an important corollary of it being true. Okay, so let's begin this claim then. So what we're going to have is we're going to have K, which is a field extension of our field capital F. Okay, so again we've got some much larger field K, which is a field extension of F. Again, it's typical to think of K as being the complex numbers and F as being the rationals, although of course this does work for 2 arbitrary fields where one is a field extension of the other. Okay, so K is a field extension of F. And what we're going to have is we're going to have some polynomial, p of x, okay, which is going to be an element of the ring of polynomials over the field capital F. So this is all starting to look familiar again. And again, we're going to insist that this polynomial p of x, or we're going to suppose rather, that this polynomial p of x is irreducible in the ring of polynomials over the field capital F. Okay, and we might also as well assume that it is of degree 2 or greater, okay, because we're not really interested, we know, in constructing a field extension where we're trying to get a solution for a degree 1 polynomial, because they already all have solutions. Okay, so we might as well assume that the degree of this polynomial, degree of p of x, is greater than or equal to 2, and we also know that we might as well assume that it's monic as well. We can always work with a monic polynomial. If it's not already monic, just multiply it by the multiplicative inverse of the leading coefficient, and then you'll end up with one that is monic. And we know that creating that field extension, which we've spent so long talking about, it won't be affected at all if we use the monic version. Okay, so we've got some irreducible polynomial p of x, which we're supposing has degree greater than or equal to 2, and which we'll also assume is going to be monic, although that's not particularly important anymore, but we can add that onto the list now. Okay, and of course that will have no roots in the field capital F, because if it did have a root in the field capital F, then it wouldn't be irreducible in the ring of polynomials over that field, because it would have a degree 1 factor. Okay, so it's got no roots in the field capital F, but here now becomes the interesting thing. Let's suppose that it does have a root in the larger field K. Okay, it doesn't have a field in the small, it doesn't have a root in the smaller field capital F, but let's suppose alpha, so let alpha be an element of the larger field capital K that is not in the smaller field capital F. Okay, and now let's suppose p of alpha, the polynomial evaluated at alpha using that ring homomorphism, is equal to 0 in the larger field capital K. Now the first thing to note, of course, is that the polynomial p of x, which is in the ring of polynomials over the field capital F, that still makes sense when viewed as an element of the ring of polynomials over the field extension. Okay, so it still makes sense to think of this as an element of the ring of polynomials over the field extension K. Okay, so that means that we can then apply the evaluation homomorphism to this polynomial for an element of our larger field capital K that is not in the field capital F, and let's suppose that we do indeed get 0. So we have a root that's in the larger field capital K but is not in the smaller field capital F. Then here comes the claim. This is the big claim. I'm now ready to state the big claim that if you generate the field generated by this root, so you generate the smallest field containing the field capital F and this root alpha that's in the larger field capital K but isn't in F, okay, and which is a root to this polynomial. So if you generate that smallest subfield, so I'll just remind you that this is going to be in between K and F here, so it's going to be a subfield in between them. If you generate that smaller subfield that contains F and this element alpha, which is a root of our polynomial, the claim is that this is isomorphic, which I'll denote like so, to the thing that we constructed, to the ring of polynomials over the field F, quotiented out by the principal ideal generated by P of x, which we know is a field extension of the field capital F, which contains a root to the polynomial P of x. The claim is that these two algebraic structures are identical, okay? That you might use different symbols to denote them, but they are identical, okay? So truly, what I want to firstly emphasize is just how deep this is and how important this is, okay, for you to understand, and then of course we will prove it. Okay, so basically this is saying is that what this is saying is that if you find some field extension of the field capital F that contains a root to this irreducible polynomial in the ring of polynomials over the field F, okay, and this is a minimal field, it's the smallest possible field that you can build that contains that root, no matter what field extension you found that root in, so no matter what K is, okay, find any field extension you like of F that contains a root. If you generate then the subfield of this, which is the field generated by that root, so the smallest subfield that contains both F and alpha, that will be isomorphic to this thing that we artificially constructed to create a field extension of F which had a solution to the polynomial. Okay, so that is quite incredible. To emphasize this even more, let's do an example, concrete example in terms of our old friends. K, let that be the complex numbers, and F, let's let that be the rational numbers. Okay, so let's take this one as our example. Okay, so we have a solution to a polynomial which is irreducible in the ring of polynomials over the rationals. Okay, so the polynomial would be x squared plus the additive inverse of 2, negative 2. Okay, that is an element of the ring of polynomials with the coefficients in the rationals. I hope we all agree on that. But of course, it is irreducible in the ring of polynomials over the rationals because, of course, this is a ring of polynomials over a field. It's a polynomial of degree 2, and we know that whenever a polynomial, whenever you're dealing with a polynomial of degree 2 or 3 in a ring of polynomials over a field, you can conclude whether or not it's irreducible just by asking, does it contain roots in the field? Of course, this doesn't contain a root in the field of rationals. There is no rational which squares to give 2. Okay, that's a basic proof well, I don't know what you call it. It's a proof that has been known for thousands of years. Okay, it's one of the proofs that you do right at the start of a real analysis course. Okay, which I won't repeat here. So there is no rational which squares to give 2. So what we could now do is we can consider generating the field, the smallest subfield of the complex numbers, which contains the rationals and the square root of 2. And what this claim, if it's true, is telling us is that the field you get, its algebraic structure, will be absolutely isomorphic, absolutely identical to what you would get if you quotiented the ring of polynomials over the rationals out by the principal ideal generated by x squared plus the additive inverse of 2, x squared plus negative 2. Okay, that's what this claim is saying. Okay, and that is quite incredible, and we're going to rely on an understanding of this from now on. Okay, so it's an incredibly important theorem. Okay, so now that we've introduced it, let's actually look at the proof of this theorem. So let's begin the proof. Now the proof isn't too difficult, but there are bits that are going to be long. Okay, it's, as I say, it's not a difficult argument at all, but there are bits that are going to require effort. Okay, so the proof of this. It's labour intensive rather than difficult. Okay, right. So how are we going to approach proving this then? So what we'd like is to have an isomorphism between these two, and I'm actually going to find a function from here to here which I claim is going to be an isomorphism. So how am I going to construct this isomorphism? Well, what I'm going to start off with is a related ring homomorphism, and I'm going to use that related ring homomorphism to construct the isomorphism from here to here. Okay, so the related ring homomorphism that I'm going to use, I'm going to call phi here, and it's going to be a mapping from the ring of polynomials with coefficients in the field capital F into the field generated by alpha over F. So it's going to be a mapping from the ring of polynomials with coefficients in the field F into this field generated by alpha over F. Okay, and how is this going to work? Well, it's going to be the evaluation homomorphism. Okay, it's going to take any polynomial here, and it's just going to map it onto what it is when you've evaluated it at alpha. Okay, so it's going to take any polynomial, and I'll denote any polynomial by little f of x, and it's going to map it onto f evaluated at alpha. Now, just to convince you that that is a ring homomorphism, because you might not be totally convinced yet, because it doesn't look like your normal example of an evaluation homomorphism. Okay, a more normal example of an evaluation homomorphism would be, okay, let's take the evaluation homomorphism from the ring of polynomials over the field capital K into the field capital K. Okay, and what you do is you just say we're going to evaluate all polynomials at some element of K. Alpha, the element that we're using to evaluate, and we could call this evaluation homomorphism if we liked, phi sub alpha, to show that the element that we're evaluating our polynomials at is alpha. Okay, alpha is going to be an element of K. This looks more strange because we're evaluating our polynomials at some element that's outside of F. Okay, and that's why this does look strange, so I need to argue this a bit more for you. Okay, so this is a normal evaluation homomorphism where you take the ring of polynomials over a certain field, evaluate them all at a certain element within that field, and of course the answers that you always get are going to be elements of that field. Okay, so this is normal. Now, what I've done is I've taken this evaluation homomorphism and I've restricted down the domain somewhat. We know that the ring of polynomials with coefficients in the field F is going to be a subring of the ring of polynomials over the field capital K. That's true simply because we know this is a ring. It's a subset of that. The addition and multiplication are identical, so of course it's going to be a subring of this. Okay, so we've now just basically restricted our evaluation homomorphism to a subring, and we know whenever we restrict a homomorphism to a subring, it remains a ring homomorphism. Okay, how could it not? How could addition and multiplication not remain compatible? If they weren't compatible from here, and imagine at the moment that this says K. Okay, I'll argue why we've reduced it just to the field generated by alpha over F in a moment, but imagine at the moment it says K, so I've just restricted down the domain at the moment. Okay, if multiplication and addition weren't compatible between the two here, then they wouldn't be compatible over here. Okay, because this is just a sub-portion of the mapping over here. In addition, the multiplicative identity here will be carried to the multiplicative identity here. Again, keep imagining that this says K. In fact, I'll write K there to stop you having to stretch your imagination. Okay, so again, the multiplicative identity here will still go to the multiplicative identity here because, of course, it's just a sub-portion of this mapping here. So this is still a ring homomorphism. It's still an evaluation homomorphism. Okay, so that's absolutely fine. Why then have I written the field generated by alpha over F rather than the field capital K? Well, because I can. I know that all the answers that I get here are going to be in the field generated by alpha over F. Okay, so I can restrict my attention down from K to that. And the reason is that all of the answers I get are going to be just powers of alpha multiplied by coefficients that are in the field capital F and then added together. Those are all operations that make sense in the field generated by alpha over F. You don't need to be working in the massive great field K to understand those. Okay? So that's why I can restrict my attention down to this subfield of the field capital K, and why I've written F of alpha here rather than K. Okay, so I hope I've convinced you that that is a ring homomorphism, and it does just take any polynomial in the ring of polynomials over the field capital F and map it onto that polynomial evaluated at alpha. Okay, right. So that's a lovely ring homomorphism, but of course I'm not interested in having a ring homomorphism from the ring of polynomials over the field F into the field generated by alpha over f. What I want is a mapping from this into this. Okay, so we're going to use this to construct such a mapping. So I'm going to call my isomorphism to be, but at the moment we're just trying to prove it's a ring homomorphism. We'll go for isomorphism later. At the moment, let's just go for ring homomorphism. Okay, I'm going to call this ring homomorphism zeta, my favourite tacky Greek symbol. So we're going to call it zeta, and it is going to be a mapping from the quotient ring, which is the ring of polynomials over the field f, quotiented out by the principal ideal generated by the polynomial p of x, into the field generated by alpha over f. Okay, and I'm going to build this, and it's going to be a ring homomorphism from this. Okay, so I'm going to use this to build this thing. Okay, right. So firstly, let me tell you how I'm going to build this. Then I'm going to have to make sure it's well defined. And then finally, what I'm going to have to do is actually prove it's a ring homomorphism. And then what we need to do, actually, that's not the final bit. Then I'm going to have to prove it's a ring isomorphism. Okay, and then of course we'll prove that these two are isomorphic. So, firstly, let me show you how this is going to work, and you can't do this without a picture. Okay, so let's firstly draw a picture of this one here. Okay, this mapping. So, this is going to be the ring of polynomials with coefficients in the field capital F. Okay, and we'll denote this in green here. Okay, and it's actually because we're going to have to do the isomorphism, sorry, the additive and multiplicative compatibility arguments soon. It's going to be a good idea to have everything color-coded in a specific color. Okay, so we'll color-code the ring of polynomials over the field f in green. Okay, and when we come on to the additive and multiplicative compatibility arguments, I will color the addition and multiplication that is in the ring of polynomials over the field capital F in green as well. Okay, right. Oh, actually, we don't need that yet. I'm about to draw on the principal ideal generated by p of x, but we'll come to that. Okay, at the moment we don't need that. We're just looking at phi here. Okay, and then our codomain, of course, is going to be the field generated by alpha over f, so f of alpha here. Okay, and we'll colour this one in an orange, I think. So here is the field generated by alpha over f in orange. Okay, and at the moment every polynomial in here is going onto an element in here in the field generated by alpha over f, okay, according to this mapping phi. What I am now going to do is define zeta. Now zeta is not going to be a mapping from the ring of polynomials over the field f. Instead it's going to be a mapping from the ring of polynomials over the field f quotiented out by the principal ideal generated by p of x, i.e. the cosets in here. The elements in here are cosets. So this is going to be a mapping where every coset is mapped onto something in here. Okay, so of course now let's draw this on. So here let's say this is our principal ideal generated by p of x. Okay, now the first thing to observe is because alpha is a solution to p of x, it's a root of p of x, then p of x is going to go onto 0 over here. So we've got 0 here. P of x, the actual polynomial p of x, is going to go onto 0. Now the principal ideal generated by p of x contains all multiples of p of x. Now, because the evaluation homomorphism is a homomorphism, when you have a multiple of p of x and you evaluate that at alpha, it's also going to go onto 0. So let me just give you the rigorous argument for that. Okay, so if you apply the evaluation homomorphism at alpha to a polynomial of the form q of x times p of x, where q of x is some arbitrary other polynomial in the ring of polynomials over the field f, then because it's a homomorphism we can split this into, using multiplicative compatibility, phi sub alpha, the evaluation homomorphism pertaining to alpha, applied to q of x, and then times, where we're now timesing in the codomain here, phi sub alpha of p of x. Okay, now why is that so nice? Well, because this is of course going to equal 0, because alpha is a root of that, and then we'll just be multiplying whatever this is by 0, so the answer will overall be 0, so this thing will be equal to 0. So actually all the elements in the principal ideal generated by p of x are all going to be mapped onto 0, so every last one of them is going to be mapped onto 0, and that should hint at how I'm going to be able to successfully define a map from the cosets in the quotient ring here onto the field generated by alpha over f. Okay, so of course, the elements then of the quotient ring here are just the cosets of this principal ideal generated by P of x. Okay, right. So let me now actually define how this mapping is going to work. So the way this mapping is going to work is it's going to take any coset containing a polynomial. So we'll say we have a coset containing the polynomial a of x. So let's say we have this coset here, and one of the polynomials it contains is a of x here. Okay, so I'll colour this in pink here. So we'll call the coset that contains it, obviously, a of x bar. So what is it actually going to be mapped onto? What is this entire coset going to be mapped onto? Well, it's going to be mapped onto what the mapping phi would map a representative of this onto. So you take a representative from this coset, any representative you like, which is why the first job we're going to have is to prove that this is actually well defined. So take any representative you like from your coset. In this case, we'll take the one that it's named after, a of x. Take phi of that, okay, which will be defined. I'm not, well, actually, I could write this in a simpler way. I could say just evaluate the polynomial at alpha. That's the simpler notation for phi of a of x, okay. So a evaluated at alpha, and of course, there we go. There, the job's finished. Okay, that's how I'm going to define this mapping from the cosets, which are the elements of this quotient ring, onto the field generated by alpha. Okay, and it's defined in terms, of course, of this evaluation homomorphism up here, which originally worked on the ring of polynomials over the field capital F. Okay, right. Now, note, at the moment, we don't know much about this. We don't know much about this. We don't know that this is surjective, for instance. Okay, that's not something we know yet. So we certainly don't know whether this is surjective. Okay, right. So we also don't know whether it's injective either. So we don't know much about this. But the first thing we need to make sure of is that it's well defined. What I need to make sure of is that each coset just gets mapped onto one thing, i.e., if you want to know where a coset is going to be mapped onto in here, it should not depend on which polynomial you pick as your representative from that coset. Otherwise, this isn't well defined at all. Okay, so that's the first thing we need to check. So, what I need to say is if I pick another polynomial that's in the same additive coset of the principal ideal generated by P of x as this polynomial a of x, does it get mapped, if I use that, does the coset get mapped onto the same element of the field generated by alpha over f? Okay, so let's take an arbitrary other element that's in the same coset as a of x. Now, an arbitrary other element will look like a of x plus, in the in the ring of polynomials over the field, some element of the principal ideal generated by P of x, which is something of the form q of x times P of x. Now note this is addition and multiplication in the ring of polynomials f adjoin x here, so I'll just put some green symbols there. This is addition and this is multiplication in that ring of polynomials over f. So I've got some other polynomial in here which is in the same additive coset of the principal ideal generated by P of x as this polynomial a of x. And I now have to ask, if I use this as my representative rather than a of x, is the answer for what zeta of this coset is going to be the same? Okay, well, what is the answer? Well, it's just going to be the evaluation homomorphism, phi of alpha applied to this. This was just the fancy way of writing that, but now here it's probably better to actually formally do it. That's the sort of more common way to write it, but this is the formal way to write it, to remember that it is actually a ring homomorphism. And of course it is a ring homomorphism, so it's going to be additively compatible and multiplicatively compatible between the two. So I can now turn this into a evaluated at alpha, and I'll use the other notation now. So it's a evaluated at alpha plus, and then we'll have q evaluated at alpha times p evaluated at alpha. And of course the operations now, addition and multiplication, have turned into the operations in the field generated by alpha over f, the codomain of the ring homomorphism, which we're denoting in orange. So I'll colour these in orange. So this addition and this multiplication need to be in orange now. Okay, right. Now, of course, P of alpha is equal to 0 because we initially assumed that that was the case. So this whole thing goes to 0, so this does indeed just go to A of alpha. So what I have now shown you is that all of the cosets, all of the elements in a coset of the principal ideal generated by P of x are mapped by this evaluation homomorphism at alpha onto the same thing in the field generated by alpha, okay, over F. And that means that it is possible to build a very well-defined function zeta which is going to map each of these cosets just onto the element in the field generated by alpha over F that all of the elements in that coset would have been mapped onto by the evaluation homomorphism pertaining to alpha. Okay, so it is well defined. What we are now going to be worried about is it a ring homomorphism? Okay, so we will have a break here, and in the next video what we will question is this mapping a ring homomorphism? And then what we'll ask is it a ring isomorphism? And if we can prove that, then we're done. We've found an isomorphism between these two, and indeed the field generated by alpha over F is going to be isomorphic to this quotient ring, which is the ring of polynomials over the field F quotiented out by the principal ideal generated by P of x. And then what we'll see is an important corollary of this.